So let's start with entropy. Entropy and lattice.
सर अभी ऑर्गेनिक नहीं की ना हमने?
नहीं, organic नहीं की. But I did it in October somewhere, but we'll obviously do it again. So we're not going to do organic yet, probably after 15-20 days, once your midterm exams are over. So so let's start with entropy. We'll quickly cover this and cover enthalpy of solution and lattice energy. So entropy is it literally means disorder. It's the, I mean, the technical definition is that it's the measure of a disorder of a system. It's a very small topic, so we'll be done with this very, very quickly. So it's the measure of a disorder of a system. Measure of a disorder of a system. So you've got ordered states, you've got disordered states. For example, there's a neat and tidy and clean room. So you're going to state that that's a low entropy state because it's got less disorder. The symbol for entropy is S. Standard entropy has a naught on top of it. The unit for entropy is joules per Kelvin per mole. So anyway, so you've got a neat and clean room, and you've got a very messy room. That's a high entropy state. So entropy is literally disorder. So whenever you hear the term entropy, that's just disorder. So, and you can apply this concept anywhere you want it on any system, whether it's related to chemistry or not. And you move things, they change states. Your room can go from a neat and clean room to a messy room, or it can go back. Now, this state is your low entropy state. That means it's got less disorder. And this other state is your high entropy state. That means, so that's your high entropy state. Low entropy states tend to be unstable. So this one is kind of very unstable. I mean, if you have a neat and clean room, that's a very unstable state because it's not going to remain neat and clean for a very long time. It quickly tends to go into a messy state. It very easily becomes a messy room. So that's kind of a very, very stable state. High entropy states are more stable. Like if your room is messy, it's going to remain messy. It's very hard to actually turn a messy room into a neat and clean room. But if your room is neat and clean, it's not going to remain neat and clean for a very long time. So that's a very unstable state. This one is a very high entropy state, is a very stable state. So things, they like to actually move towards high entropy state, towards more disorder. I mean, this arrow is more likely to happen. I mean, it's 100% more likely to happen. There's a universal law that things tend to gain disorder, and it's easier for them to gain disorder. It's a lot harder for you to go in the backward direction. That requires, I mean, this arrow over here is difficult, so we can write difficult. And this other one over here is easy. That's easier to happen. And there's a thing called delta S. That delta S, and if it's got a naught on top, that's standard. That is the standard entropy change. I mean, if you just remove the word standard, it's just entropy change. So it's standard entropy change. And it's got two signs. Delta S could be positive. So when it is positive, that means there's a gain of entropy or there's a gain of disorder. And vice versa, delta S could be negative as well. That indicates that there's going to be a loss of disorder. So it's going to become more ordered, or there's going to be less disorder. So it's going to be a loss of disorder. So it's got these two signs: a high entropy state and a low entropy state. Let me see if I can. So it's got these two signs. Delta S positive and delta S negative. Now this one over here, the easy one, delta S positive is easy. So this over here is delta S positive. The change is positive. There's a gain of disorder. And the difficult part is delta S negative. That is slightly, it's more difficult to happen. So remember, around you, everything likes delta S positive. Delta S positive is more stable. It results in higher stability. Delta S negative results in lower stability. A neat and clean room is less stable. A messy room is more stable. A messy room, even if you don't do anything, it remains messy. So that's a very stable state. A stable state is one which maintains itself. So a messy room, no matter what you do, it always remains messy. It's not magically going to turn into a neat and clean room. So that's one thing. That things like high entropy. Is this clear? This first thing, this first concept, are you clear?
Yes, sir.
Yes, sir.
So then we have the other thing, which is let's apply the same thing to chemistry. Now, the first thing is, does anyone have any idea why this is more stable? Why is high entropy state more stable? I mean, why is your messy room more stable? Like, why does it remain messy? Why doesn't it automatically turn into a neat and clean room? I mean, your neat and clean room automatically, you don't do anything special. It by itself turns into a messy room. But the other direction doesn't happen. Your messy room does not by itself. If you just don't do anything, your messy room will not turn into a neat and clean room. So what? Why is that? Why is a messy room more stable? Any idea? कोई भी नहीं बात का any idea?
Because in order to turn it into a neat and clean room, we would have to work and like give energy or something.
So I know that's difficult. It's very difficult to actually make it into a neat and clean room, right? But to turn a neat and clean room into a messy room, that's very easy, right? You don't even have to do anything. It just turns into a messy room by itself. What I'm saying is, why is it that this is more stable? Why do things want to get messy? Okay, if you have a house and let's say somebody abandons it, what happens to it? Even if no one does anything, over time, it's going to turn into a very disordered state. So the question is, why is there a universal law which favors disordered states? So the thing is that disordered states have higher probability. They have 100%, almost 100% higher probability. Like ordered states have almost 0% probability. So disordered states have much higher probability. And ordered states have very low. So ordered states have very low probability. So let's imagine you have thousands of different states. Like let's imagine your room. How many ways can you put it in an ordered state? There are very few ways. Like if you want a neat and clean room, there's just a limited number of states where you could turn it into a neat and clean room. How many ways can you make it into a messy, untidy, disordered room? There are millions of different ways in which you can make it into a messy room. So the thing is that the number of probable states for a messy room, they are almost infinite. There are infinite possible ways where you can make something disordered. I mean, look at your car. If you have a car, there's only one way in which it's going to work exactly right, where everything is ordered, where all the nuts are in the right places, the engine is in the right place, the tires are in the right place. So there's only one state where the car is going to function, and that's going to be your ordered state. How many ways can you like make a car disordered? There are millions of different ways. Like if you want to break it apart, if you want to turn it into a disordered state, there are millions and millions of different ways you can do that. So the probability of having this messy or more disordered state, that's really high, which is why things, they tend to turn into over time, they turn into a disordered state. I mean, your car will over time break down. This is not going to happen that you buy an old car and over time it's going to turn into a really perfectly fine working car. That's not going to happen because there's only one way in which the car is going to work, and there are millions and billions of different ways in which the car is going to be in a disordered state. So eventually the probability of being in a disordered state is a lot higher. Is that point clear?
Yes, sir.
Yes, sir.
Okay, so remember, the universe favors disorder. It likes to keep things in maximum disorder, and the more you use something, the more disordered it's going to go. I mean, if you keep using your car, it's going to become more and more disordered over time. So everything likes high entropy. All systems, they like high entropy. They don't like low entropy. It's not about likeness. It's very hard to actually maintain low entropy states because there's so few in number. Now, let's put this to chemistry. Remember, delta S positive means that there's a gain of disorder. Delta S negative means there's a loss of disorder. So the first question that you're going to get is predict the sign of delta S. And we're going to move towards chemistry now. Okay? So entropy literally is disorder. So if you have a chemical reaction going on, by just looking at the chemical reaction, you would get an idea that is delta S positive or negative. So predicting a sign of delta S by just looking at the equation. So first one, option number one, state changes. So that's the first one. Now in changes of state, you've got solid ice. Let's say there's a beaker and there are 3 of them. So here's another one. Actually, I've got 3. I've got 3 beakers. And so the first one has ice in it. So it's completely frozen and there's water in the state of solid ice. The second one has liquid water in it. And this third container over here has the same water, but now it's in the form of gas particles. So all the molecules are randomly, they're just flying about. So which one do you think is the more disordered state or high entropy state? Which one is it? Higher entropy.
Sir, gas one.
Okay, so gas is obviously your more disordered state. So remember, the first thing is changes of state. Whenever you see a change of state happening, things are moving towards, and especially if it's from a liquid to a solid to a gas. So that means its delta S is positive. There's a gain of disorder. Over here, there's a gain of disorder again. Where do you think is there a larger gain of disorder? Solid to liquid or liquid to gas?
Liquid to gas.
You guys remember, liquid to gas is a much bigger, it's a larger increase in disorder. This one is a much larger. The amount of disorder between solid ice and liquid water, that's not that large, although there is disorder, but it's not that large. So this is how your entropy or disorder would change. So if I were to plot a graph of entropy change with respect to time, or with respect to temperature, how would the graph actually look like? So it's going to look something like this. This side is entropy S. So it's going to look like something like this. It's going to be almost constant, and then there's going to be an increase in disorder, and then it's going to be almost constant once more, and then there's going to be a significant increase in disorder. So it's kind of going to look like this. This is going to be 0 degrees centigrade, and this is going to be 100 degrees centigrade. And it's going to be a vertical line because just a second. So, I mean, the change would almost be vertical because the state change happens at constant temperature. But anyways, so most of the disorder, the change in disorder happens when there's a change of state. Over here, it's solid. Then over here, it's liquid. And over here, this is a gas. So the disorder continuously increases. One thing that happens over here is after gas, there's going to be a much higher, let me move the graph. So after gas, this one is, so in gaseous state, the disorder increases. But anyways, one by one, we're going to talk about this. First thing, once the ice is solid, it doesn't really matter what the temperature is. The disorder kind of remains constant. I mean, it almost remains constant. Like, would there be any visual difference if the ice was at minus 10 degrees centigrade, or whether it's minus 50 or whether it's minus 100? It's going to remain pretty much the same. The order or the disorder would kind of remain exactly the same. Is that point clear?
Yes, sir.
Yes, sir.
Okay, so remember this, that once it is solid, the disorder is going to change, but very slightly. You're going to increase temperature. So if your ice was at minus 200, now it's at minus 10. Maybe one or few molecules might evaporate, or there's a very low probability of that happening, but or they might change into liquid state, but they might gain, a few particles might gain energy. So the disorder would increase, but very slightly. I mean, there would be hardly any noticeable change. The same applies to liquid water. Like if the water is at 10 degrees centigrade and the same water is at 50 degrees centigrade, as an observer who's standing there, you will, by just visually looking at them, there would be hardly any noticeable difference. Okay, imagine there's hot water and there's cold water. As long as it's liquid water, visibly there's nothing happening. The disorder is kind of almost the same. Is that clear?
Yes, sir.
Yes, sir.
But for gases, remember for gases, it's not going to be exactly the same, because in gases, the temperature really matters, because imagine a gas at 1000 degrees centigrade, and there's a gas, let's talk about steam. Imagine steam being at 1000 degrees centigrade, and imagine steam being at 120 degrees centigrade. The amount of disorder that 1000 degrees centigrade is going to cause, that's going to be significantly more. I mean, you see those car radiators blowing up if the engine heats up, right? So there's a lot more disorder. So remember, for gases, in liquids, it's not going to be that much of a difference. I mean, this, and same applies to solid, but you can't say that for gases. Is that clear?
Yes, sir.
So gases are not, the disorder is not going to remain constant with temperature. And the reason is that gases expand with temperature. So they're likely to cause a lot more disorder. Liquids don't expand when you increase temperature. Like if water is at 10 degrees centigrade, it's 50, it's still the same liquid, nothing happens to it. So gases, they expand. They expand when temperature increases. So which is why as the temperature increases, there's going to be a lot more disorder, and the disorder would continuously increase. So the gradient would be a lot more. Over here, it's going to be almost constant. Over here, it's also going to be almost constant. So is this part clear, this thing?
Yes, sir.
To give everyone else, Nadine, is this clear? Zahib, Sumaya, Minahil?
Yes, sir.
Yes.
So next is, okay, you've got, so remember this thing, and also remember one thing, that the solids and liquids, they don't create a lot of disorder. I mean, that's obvious. I mean, you look at ice and you look at liquid water. They don't create a lot of mess. They don't create a lot of disorder. But steam is going to create a lot of disorder. Okay, so whenever you have steam, it creates a lot. So this one is, the amount of disorder is significantly larger. So remember this, that gases, whenever gases are involved, a lot more disorder is created. So number two, one is change of state. So whenever you see that happening, that's a gain of disorder. Number two is in a reaction. So now this is about reactions. Whenever moles of gas increase, so whenever moles of gas, they increase, disorder is going to be created. Delta S would be positive. And remember, the reverse is also true. If I mean, the opposite is also going to be true. Delta S would be negative. So whenever you have moles of gas increasing, for example, I've got PCl5. Yeah, let's take PCl5. Let's say all of them are gases. I heat it and it decomposes and it produces PCl3 plus Cl2. And let's assume the temperature is very high and and all of them are gases. So all of a sudden, one molecule has turned into two molecules. It's split up and it has turned into two molecules. So there's going to be a lot more disorder created. You had one molecule, now you've got two molecules. So you had this one molecule, which was PCl5, and it split up and it broke into two tinier molecules. One of them was PCl3 and the other one was Cl2. Now, these two smaller molecules are going to create a lot more disorder. They're going to bump into things, they're going to push on things, and they're going to exert pressure. And there might be an explosion, like if these two particles would be able to break through a wall of the container. So, and exert enough pressure to break that thing. So a lot more disorder would be created whenever the number of moles of gas they increase. Is that clear?
Yes, sir.
But similarly, we can have a decomposition reaction. You've got calcium carbonate. And calcium carbonate is reacting to produce, you decompose it, It produces calcium oxide plus carbon dioxide. So again, the moles of gas are increasing. So disorder is created. And why? So this is, both of these are delta S positive. And the first one is also delta S positive. And we can have the other way around as well. Like if you have the Haber process, N2 and H2, they react together to produce, all of them are gases. So they react and they produce NH3, 2 molecules of NH3. And NH3 is a gas. So when this happens, the moles are decreasing. You had 4 moles of gas, and now you have 2 moles of gas. So that means delta S over here is going to come out to be negative, right? So is this clear? The second point. You clear this, Arako?
Yes, sir.
Yes, sir.
Now we have the third point, which is, the third one is a dissolving. That's one example. Let's say you're dissolving something, and so obviously that is a gain of disorder. So calcium chloride, that's solid, and you mix it in water and it becomes aqueous. So automatically the particles are now mixed in water and there's a lot more disorder. Previously they were a fine solid, tightly packed, but now they have dissociated ions, dissociated and scattered ions. So that's delta S positive as well. Number 4 could be that if the states are the same, if same states, then you look for the number of particles increasing. Like even if it's a solid and the number of particles they increase, or if everything is aqueous and the number of particles increase.
Sir,
Huh?
could evaporation, like if we're evaporating the solution, could that be delta S negative?
It's going to be delta S positive. Okay, when you
Evaporation, like
evaporation is the change of state now, so it's solid to liquid to gas.
no, for this CaCl2, I mean, it's coming back into its solid form. Water is escaping.
If you're evaporating this, as it's coming back, crystallization.
Yeah.
Otherwise, that's delta S negative if you're doing the reverse.
Okay.
Achha, if same states, number of particles they increase, but the states are the same, like all of them are aqueous, then that is obviously delta S positive. If you have more particles, there's going to be more disorder. So that's definitely delta S positive. So I'll do an example of so we can do one aqueous state. I mean, what could be an example for this? Same state, but the number of particles they are increasing. Or we can do the opposite, like you add H+1 to solution and you add OH into solution and they react together to form H2O. So aqueous and liquid states are kind of the same state. So over here, it's clearly that the disorder is decreasing. So delta S over here is going to come out to be negative. So that's the first question that they're going to ask you. Whether delta S is the entropy change positive or negative. So most of the time you can just look at the reaction, you'll be able to figure this out. So I'll just do some past paper questions on this specific thing. So just on the sign, now over here he's saying explain why the entropy change for reaction 1 is negative. So you've got reaction 1, which is over here. Why is the entropy change sign negative? Why is that? Why is the disorder decreasing? What could be the explanation for that?
Less number of moles are produced.
Or you can say that there was gas and now you've got a liquid. So the moles of gas over here, they decrease. So your molecules of gas, they decrease. There was a lot more disorder initially because there was gas, and now there is no gas. Is this clear why this is negative, right? Clear?
Clear.
So this one is, we can do this one. I think we can. He's saying the delta is for addition polymerization, delta is for condensation polymerization. Slightly difficult because it involves organic chemistry, but we can do that. So there's polymerization happening. So he's saying addition polymerization. So you have to tell what the sign is. So I'll explain what's going on. There's CH2, double bond CH3. So this is addition polymerization, just like in O levels, in AS, I think as well. So what happens in addition polymerization? You've got lots and lots of molecules, which are monomers, lots of them. And what happens? They all join up, right? So the double bond between them, it breaks. And all of them, they start interlinking with each other. They start making bonds with each other. So in this case, they all link up, right? So this is what's happening, what's going on. Can you tell me what's happening to delta S? Was there more disorder previously or less? Is it moving towards lesser disorder? Delta is negative or delta is positive?
Negative.
T8 is negative because previously, let's say you had 1000 molecules, right? And those molecules were all randomly flying around. They were probably in gaseous state because these are small organic molecules. So you had 1000 molecules and they were all randomly flying around. And all of a sudden, they all joined up to form this single chain. And they ended up forming, let's say, just one molecule. So that's a lot more that's a lot less disorder. So that is definitely delta S negative. Is this clear?
Yes.
Is this clear to everyone?
Yes, sir.
I said, then what about condensation polymerization? What happens in condensation polymerization? Now I'll explain first. This is like your O levels. You had a molecule, a monomer, which is, or maybe I'll just see if there's a Google image on this. So I don't know why. Just 1 second. Let me just. So condensation polymerization, if we have. Isn't there a simpler? I forget this. I'll have to draw this. So this is what condensation polymerization from your O levels. You had an alcohol and it just continuously repeated. You had a carboxylic acid and you had an alcohol. Then you had another carboxylic acid, which had carboxylic acids on both sides. And after that, you again had an alcohol and it just continued like this. What would happen is that the H and OH in the middle, they would form water. So the OH and H would be lost. The OH and H would be lost. The OH would be lost here, over here. So they're going to form water, and this is what would be left in the middle. It's going to be So this is something that would be produced. But every time there's a link created, there's going to be a water molecule that's going to be produced. Over here, there's going to be a water molecule that's going to be produced. On this side, there's going to be a water molecule as the link is created over here. There's going to be a water molecule that's going to be produced. So what do you think? Is the disorder increasing or decreasing when this happens? Does the number of molecules, it's increasing because the number of molecules, they increase. If you have more molecules, there's going to be more disorder. So the number of particles, they increase when condensation happens because lots of small water molecules are produced as a result. And which is why delta S in this case would be positive. So what you're going to, I mean, you're just going to write a simple explanation for this, which is going to be in the first one, you'll just state that thousands of molecules join up to form a single molecule. So the number of particles decrease and there's a loss of disorder, or delta is negative. Over here, molecules join up to create water molecules. So the number of particles, they increase, which is why although they join up, but they produce a lot of small, tiny water molecules, which is why the disorder increases. So the number of particles increase. Is that clear?
Yes, sir.
Yes, sir.
So we're going to do similar. So this one, what is this one? Delta is negative or positive, this one?
Negative.
Negative.
Because you had a gas and it turned into a solid, so disorder is decreasing. So that's negative. What about the third equation? There's a solid crystal which reacts with liquid
Negative.
water. And so the liquid turns to solids, that's negative. What about this one? It's solid, aqueous, gas, liquid.
Positive.
Positive.
Okay, so whenever a gas is created, there's going to be more. Whenever the gas moles increase, there's going to be more disorder. Then we can have just one more question similar to this, and that's just a second. This one is kind of magnesium reacting with hydrochloric acid. What is the sign? I mean, for this, you need the reaction. Magnesium reacting with HCl, it would produce magnesium chloride plus H2 gas. So what's going to happen?
Positive.
Because a gas is going to be created, so that's a gain of disorder. Potassium chloride dissolving.
Positive.
Okay, that's going to be positive because KCl was a perfect crystal and then you mixed it in water and the ions, they all got scattered in water. So they turned into dissociated aqueous ions, and that's why. So in this case, the explanation would be that the ionic lattice KCl dissolves and dissociates in water. So which is why steam condensing to water, what is that?
Negative.
The gas molecules, they decrease. I mean, there was a gas and that turned into liquid water. So we'll cover the next thing. That's the first thing. The first thing they'll ask you about is the qualitative assessment, whether delta S is positive or whether it's negative. Okay. So let's continue tomorrow now. Okay, clear? Is it? Okay. Take care, Allah Hafiz.
Thank you, sir. Allah Hafiz.